Thank you, and I hope we can talk okay to hear me. I've been around the sun a few times, so I got a little gray hair and don't walk as well as I used to. But I'm still in touch with electronics, and that's been my love of life. Anyhow, back in the late 90s, I got this call from out in the blue about this guy named Russ. He says, I got a tag, but the interphone system doesn't work. And he wanted to know if I could fix it. And I said, well, gosh, I don't know. I don't even know what an MFI tag was. He says, well, I've talked to people around Loveland, and they all said that you could do it. So I said, all right, I guess I will. So anyhow, the interphone system in a tank, this is an M5 tank. This is the control box or box for the workers or the crew members. And the crew members each had a headphone and a microphone, because inside a tank is pretty noisy, I guess. I've never been in one when it's running, but I'm sure it probably is. Okay, next. So we'll go along with a little bit of touch of history. The Signal Corps became an official communications arm of the military during the Civil War, and they used flags to send and receive magazines. You know, the wigwam, the Boy Scouts used to teach. So they've been around a long time. One of them, and they were very progressive, so they went from flags to telegraph to radios. And Edwin Armstrong, I don't know if you know him, but he was the captain in the Army, and he invented the super heterodyne radio in 1918, which is the basic format of radios until digital radios came by a few years ago. He also invented FM, which proved to be very effective in 1933. Signal Corps developed most of the World War II communications equipment. And of course, the Signal Corps was not a design and development place. They would contact companies like RCA and Motorola. Of course, Motorola didn't exist at that time, but Galvin. And they actually did the design. But Signal Corps was in charge of how the design would be and in the production. So one of the sets they had designed before the war was a 100 megahertz SCR-193 radar, which detected the aircraft in Pearl Harbor 45 minutes before the event. Of course, as we all know, the warning wasn't needed, and we know of what happened. Okay, next. So this is a picture of the radar set installation, and the antenna rotated about 1 revolution a minute, and it took 2 people to run it. One person looked at the oscilloscope, which would look at the time domain radar, which was known as the A-scan, and then another person had to look at the antenna and see where the compass said it was. So it's kind of a cumbersome setup, but it worked. The Signal Corps had a numbering system that they used the radios and radar, and they call them the SCR numbers, which meant that's what all the equipment it took to set up the stuff. But the actual individual equipments had BC numbers. So SCR stood for Signal Corps Radio or Set Complete Radio. In literature I've read, I'm not sure which is correct, but I like the phrase Signal Corps Radio. Go ahead. So a little bit on the technology. If you look at the manuals for World War II stuff, you won't see terminology the same as they're there today. So so at that time, they didn't have hertz, so they used the symbol C. So they would say 100 kilocycles, not kilohertz. And of course, that was theoretically incorrect because kilocycles is a time domain number, and frequency domain hertz of cycles per second. And the SI units, as we all use today, came about in 1963, which is when I graduated from the University of Illinois. So all my textbooks was not with SI units, so I had to learn SI units just like everybody else in my engineering at HP. And also the SI units, they got names for small value capacitors like micro. That's what they used to say. If you look at the manuals, they'll say MMF. And of course, they coined the prefix pico for 10 to the minus 12th, and a lot of other terminology like 10 to the minus 9th was nano. Next. So during the World War II, the only active technology was vacuum tubes. And tubes were developed for all kinds of functions and RF circuits, CRTs, and amplifiers and that sort of thing. They came in all kinds of sizes and shapes. And I thought there was a picture with that, but I guess it's missing. And tubes were manufactured in large numbers, and they're still available today. And they're known as NOS, or old stock. In the military equipment, the tubes were numbered as VT- such and such instead of the typical commercial number like 6V6. Next. So I don't know what happens to the picture here, but in here would be a picture of a I-77 tube tester, which was used by the military during the war too. Okay, receiver tubes had kind of two basic ways of operating. They had the most common for receivers and everything, they had a cathode element which emitted the electrons. Transmitter tubes were usually different because they had a directly heated filament. In other words, no indirectly heated cathode. And so when the transmitter tube filament was lit up, it was ready for operation. And so that enabled transmitters to be not powered up until they were actually used, and then you would get almost instant on use. So this was very important for the transmitters at that time. And the high voltage was generated by a dynamo or vibrator. Next. The BC-191 transmitter used 4 VT4 vacuum tubes and was rated at 75 watts. Filament power was at 3 amps at 10 volts, so there's 30 watts of power just to light one tube. So it had 4 of them in there, so 120 watts just to light the tubes. So I had a Hickok tube tester, which would test most tubes, but I had to make, in order to test the VT4 tube, I had to make my own system of testing the tubes. And gosh, this picture, oh, she was missing. Okay, go to the next slide, see if it shows up. Oops, no, go back. Anyhow, in order to test those tubes, I built our own little system by having a power supply for the plate, the grid, and the filaments. And then I used the manufacturer's plate current versus grid current, grid voltage, and could evaluate whether the tubes were good or not. And of course, in the picture, I had HP test equipment. And of course, I said, you can only do this with HP test equipment, of course. Okay. So generating high voltage was sort of a big deal during that time because the vacuum tubes required voltages for usually from around 200 volts to 2,000 or 1,000 volts. So they had two main means. One was with the vibrator, which was actually used in car radios even before World War II. So the vibrators was used to generate high voltage a number of times, and the vibrator inside looks like that. And there's a little vibrating element that would go back and forth and generate approximately 100 hertz tone. Chopped signal into a transformer which would then step up the voltage, and it would be rectified for the tubes. Next one. So my friend Tom and I, those vibrators usually all failed because the components, the contacts got corroded and everything. So we went to solid state units, and so we made up a PC board with 2 big power FETs and an oscillator to simulate the vibration, and voila, there we had our vibrator, solid state, reliable. Go ahead. So generating a high voltage was mainly done with dynamotors, because dynamotors were very efficient. They were kind of heavy, but they were very efficient at generating. A dynamotor is a unit that has 2 windings. So here is the primary that would run the motor, and here's where the generator part was. And that would generate the high voltage. And they came in lots of different sizes, small ones for receivers. This is for a moderate sized transmitter. This would be for a higher power transmitter like the BC-191. Okay. Although radar was probably the most important technology developed in World War II, the development of FM communications was very significant for the mobile armored units. The ability to communicate in the presence of ignition noise was an advantage over AM system, and really made it a communication advantage for the military at that time. FM transmitters were actually PM, phase modulation transmitters, as they used it described in the manual, a non-linear coil phase modulator. It was really kind of a special made coil. I really kind of struggled trying to understand how it really worked, but it did work. So FM transmitters in the tanks at that time and other armored vehicles operated in the 20 to 27 megahertz range, and the artillery operated typically in a higher range above it, 27 to 39 megahertz. I should be using KC, but I got hertz on my brain so much that I can't go back. The regular Army and infantry typically used AM transmitters in the high frequency range. Next. Component part failures. Okay, I believe that during World War II, the failure of these radio transmitters was very minimal because they were so well designed and built. But after the many years, it's like 80 years now, when I started restoring these radios, I discovered that the thing that's usually always bad with them is the capacitors. So here's paper capacitors in the radios. And it took a lot of effort to get those out because they would wrap those wires around the terminals and they were securely soldered. So it took a lot of solder wick and a lot of twisting on the pliers to get them out. And then I would replace them with brand new film capacitors, and that was easy. And here's a box of some of the parts I saved that I replaced. And I used, even though I had a Heathkit capacitor tester, which is really the only type of capacitor tester you could use to test those things, because most of the newer capacitors meters, they only put a volt or two or even less across the capacitor, so you'd never know whether there was actually failed or not. But with the Heathkit tester, it would apply hundreds of volts like it normally would use, and they would show up. So I just out of fun, I tested virtually every one of the capacitors I took out. I never did find one that was good. Go ahead. So here's one of the basic sets that are used in the tanks, and it was called the SCR-508 set. And as I mentioned it before, SCR meant this is all the stuff it took to make a radio transmitting system in the tank. And so it was used in almost all the military tanks and other vehicles of that type, like armored vehicles and armored cars and so forth. And the SCR set also provided the power and the radio connections to the tank interphone system. And the radios were mounted on radio on mounts. Almost all the military radios had mounts for the radios. And some of them were sophisticated, some of them were just mounts where the radio just set on so that it was easy to take the radio in and out of whatever it was installed in. So the unit over here, this is the BC604 transmitter, and these two are the two receivers. And the reason they had two receivers, as I understand it, is that of course they couldn't scan. So if the tank was maybe the main command tank, I assume he was requested to listen to his own tanks on one receiver and listen to some other command tank on another frequency. So they had to have two receivers in order to do that. So, and then of course the BC604 would run the interphone system for the operators and the crew members in the tank. And of course the numbers were different, 528 and 538 for different combos of the thing. So you may have noticed this little box right here. This is what they called a phantom antenna, which was used to tune up the transmitter. They didn't have dummy loads in those days, as far as I could tell. They used what they called phantom antennas. Actually, it was a capacitor and a resistor to simulate vertical whip antennas, which was the typical case. On that, oh, thanks, Durbin, I think.
Late 60s. Late 60s, I was a new ham. And one guy that was a seasoned extra class older ham gave me one of those receivers. And that was my first 2-meter FM station. And I had a different box as a transmitter, an old Motorola thing as a transmitter. And it was a 27 or 29 megahertz as described. So you had an up converter, down converter to bring 147 megahertz down to 27 megahertz and pump it through that thing. And that was my first amateur 2-meter FM station. That's when repeaters was a whole new concept, and there were a tiny few.
Okay, this is probably the most complicated mount that was used in the radio systems like that. And so you could plug in the transmitter, the antenna was hooked up over here, the receiver's plugged in down here, the cables came in on this side, and then underneath this compartment is where they're all terminated. So the transmitter and the receivers could be plugged and unplugged without having to be figuring out how to connect the actual wires to the units. And here's another little pictorial thing in the wires here and that. So that was complicated, but almost virtually every radio at that time mounted on a mount, and this was the most complicated one that I came across. Go ahead. So the BC603 FM receiver right here had push buttons similar to the car radios of the 50s. It was a continuous received radio, so there wasn't any crystals involved. And there was a dial and so forth. They had a standard volume control, squelch control, and that sort of thing. And they were very serviceable. For example, the front panel could be taken off, and you could service the switches, and the speaker here, which, by the way, the speaker was a number of speakers were failed because I think they got wet or damaged or somehow. So it did replace the number of speakers. And the other thing to note is this stuff is heavy, 35 pounds. So go ahead. The receiver inside, here was like the push button turning thing, the dial, and here's all the transformers and the tubes on this side. You could kind of say, okay, this is the component side of a PC board, and here's the circuit side. So here's where all the wiring was. This is the dynamotor, and the yellow ones are all the capacitors that I replaced. One of the things that's nice, the military had a little adapter block that you could plug into the back of the receiver, supply power, and also do some testing. So that worked out very well. So I didn't need to have the mounting hardware to run it. Go ahead. So the transmitter was crystal controlled at 10 channels and operated 20-28, power output of 25 watts, weighed 67 pounds, and the T17 microphone, of course, is the universal microphone of that time. Virtually every transmitter and almost all the services use it. I mean, that T17. The company who made those probably make a nice profit. In this compartment here, it held extra crystals so that the transmitter crystals could be changed to different frequencies. Here is the crystal department, and this is where the lid is off. So they thought of a lot of stuff at that time, because there's on the side are two resistors with a thermostat, and that thermostat would make those heaters come on when the transmitter got cold. So I was thinking they were worried about the crystals, but what about the poor crew people? And of course, here is the meter, which could be selected by that, and it would show RF current when it was in that position, or other currents in the unit. Go ahead. Next one. Okay, before we leave the tanks, I found this on the internet. I would help to remind you, tanks are really big. I don't know if you've been around tanks, but they're not very small. So I can imagine during the war that the Jeeps would zip around and the tank wouldn't see them. And so they had a speeding problem. And of course, I'm sure the tank won every time. And maybe we should have some signs like this around town, slow people down. Go ahead. So here is a typical HF transmitter receiver setup, the SCR-193. And this is the BC-191. Here's the phantom antenna up here. And then over here is the receiver, the BC-312. Down below is the dynamotor DB77, and a speaker down here, LS3. The receivers are all basically designed to run off headphones, but they did have speakers that would run that. Go ahead. So here's the transmitter again, another picture. It could operate from 1.5 to 4.5. I got it right, megacycles. And with the different tuners down here, they had a whole series of tuners that would cover the different ranges. And the tubes in here was a number 82 for the microphone. This was the oscillator tube. This is the power out tube. And these two tubes were the plate modulated for the AM part. So this transmitter was a very good sounding transmitter, and I never did actually try to use it on air, but I assume some people did. So, and so it was fully metered. So here's the plate current meter, filament meter, an ammeter over here, and here's the built-in tuner. They had built-in tuners at that time too. And it's a roller inductor and a controller and the capacitor here and other switches. And in the manual, it would tell you how to place these switches for different types of antennas. And of course, the vertical was the standard that most people used. And also, since there was no VSWR meters at that time, you would always tune for maximum RF current in the RF meter. Virtually all the transmitters had RF ammeters in them. Go ahead. I don't know why some of these pictures don't come through, but anyhow, this is a picture of the back of it where you could see the roller inductor and so forth. And here's the tuner, where the tuner was removed. In this case, there was a fair amount of mechanical work because all these banana jacks that are underneath here, they connect to the tuner. Most of them were defective. They had gotten bent, so somebody had tried to put the tuner in incorrectly or something. So that was kind of a mechanical job to get that done. Next one. So here's the roller inductor. I'm sure maybe some of you old timers remember seeing the roller inductors, which were valued things. Here's the RF ammeter and a big switch, and underneath here would be the variable capacitor. Most of the capacitors we just took out or replaced, but in this transmitter they had this multi-element capacitor, and much to my amazement, it was bad. So me and my friend Tom got together, we removed it, he unsoldered this can, removed it, and I bought regular capacitors to put it in, and we put it all back together, and it looked just like the original. So typically we didn't do that kind of effort, but I thought it was worth it. Go ahead.
Hey, Virgil?
Yes.
Even today, amplifiers have roller inductors in them.
Is that right?
And you're encouraged every so often to grease them or
Yeah.
lubricate them? Did you run into that?
I don't know, it all worked. I didn't do anything to them. Okay, here's where I have it all apart. Here's the strip that held all the banana plugs and all the things. So it took a while to play that. Next one. Okay, I got things all back together here. And here's a picture of the transmitter actually functioning. And here's the plate meter, so you can see it's reading, and a filament voltage meter. And so they use the resistors to reduce the current to the filaments, to the tubes. So they had a voltmeter there. And on top here, there was a variable resistor. You could select taps. So that was a function that you could actually do. And then here is the RF ammeter showing that it was reading, and the units for doing the tuning the antenna. So the phantom antenna, they all consisted basically of a variable capacitor and a 6-ohm resistor, because verticals are typically capacitors with a small resistance, radiation resistance. So it did a pretty good job of simulating an antenna. But of course, the operator would, when the actual antenna was connected, would obviously touch up those controls. And so when the transmitter was operating, it drew 35 amps. So I had a 60 amp power supply, but it wouldn't start a dyno motor. If any of you remember old cars with starter motors, unless that battery was in good condition, it never started. Well, these dyno motors were like a dead short, so it had to supply tons of current to get them moving. So I had to put a battery in series or in parallel with the power supply in order to start it. My power supply would easily run the transmitter, but would never start the dyno motors. Go ahead. Next one. Okay, the BC312 was a very sophisticated receiver for that time, and it had a tuned RF stage and 2 IF stages. It was very selective and good image rejection, and very sensitive. I mean, I don't remember the numbers exactly, but with my signal generator, it received signals way down there, so it was very good. And it was, of course, designed to operate with CW. CW was used by the military probably as one of their primary communication means with CW. Thing weighed 58 pounds, and by the way, when I did this, that was about 10 years ago, I could actually lift it, but I can't lift it anymore. The dynamotor was small. It only drew 2.7 amps, and my power supply would easily start it up even without a battery hooked up. Go ahead. So here's some more on the inside of it. So this is where the dynamotor set was inside this can. And these are some of the IFs, the RFs in here, and the oscillator for the local oscillator is on this part. Here's where the dynamotor, this is upside down. The dynamotor was set in this area here. Here would be the RF shielded boxes for the RF stage and the mixer stage, and shielded for the CW, or for the RF oscillator stage. So they were very well shielded, and they had performance was really equal. So one of the things I noticed when I was working on these radios, virtually all the receivers that I looked at all had tuned RF stages. And I kind of wonder why the military wanted to have tuned RF stages for the radios. I mean, that made for extra selectivity for the radio, but I kind of wondered. But then I read someplace where a military and the Signal Corps made that a requirement because they didn't want these receivers to be noticed and detected by the enemy. So they wanted to make sure that these radios would not emit spurious responses while they were receiving. So whether that's true or not, I don't know, but it certainly is true that the RF stage would almost virtually eliminate the receiver broadcasting the signal back into the antenna. Go ahead. So here's the inside of one of the RF stages, and look at the mechanical construction. RF trimmers at that time were stable, and these coils were all wound. It was amazing. Here's the capacitors that reflect the little white things there. It was kind of a struggle to get to those because I assumed when they were built, these capacitors were installed first and then the rest of the stuff. Well, so I had to be pretty twisty to get those things out. Here's inside the RF oscillator cavity, the tube, the radio capacitor, the oscillator tube, and all the associated circuitry. Go ahead. So here's all the RF tubes. This is the one receiver that's, for some reason, these capacitors for the RF stages, they were all bad. And they were oil filled, which typically were not failed. So I don't know whether the manufacturer built those, didn't know what they're doing, and they all failed, but anyhow. So I just left them in place, and underneath I put the smaller capacitors and resistors. This is inside the BFO section, here, right here, and one of these capacitors is connected to the knob to the front panel. And there's one of the tubes and the volume control. I don't know if maybe you can't read it, but I know where you can a little better. They would always print on the equipment the R numbers and the C numbers and that sort of thing. So if you saw the manual C number, you could find it by just looking in the chassis, and you would find it. Go ahead. This is another view. This is before I restored this one. So this is inside the compartment where the dynamotor is located, and here's where all the wires to the dynamotor would be connected. Here's some of the connections for the receiver's transmitter, microphone, and the receiver headsets. Go ahead. So here I got it all restored. And an interesting thing that I never did really get an answer for, but there's what appears to be a coaxial connector there. But I never did see anywhere in the literature a mating connector. And of course, at that time, coaxial cable was really a rarity, but it was, well, the radar people, I think, is the ones that developed coaxial cable. But for the regular HF communications, there was no such thing as coaxial cable. But if I looked at the manuals, how the set was connected up in the systems, they all used this push-on antenna wire connector. So somebody had a good idea, but they never got to see the fruition of it. So here was the antenna trimmer connector. Here's the dial with the light in, and a dial which you could adjust the brightness of that with, the volume control. Over here is the band selector, where you could select the KC bands. And here's the main rough coarse tuning knob and the fine tuning knob for the receiver. And then over here was the jacks for the microphone and the earphones. The main connections. So there was no microphone here, of course, but this set was designed to operate with like the BC-191, where you could have this cable would carry the microphone signal over to the transmitter. So you could operate the receiver and the transmitter from this same location like that. The receiver speaker on top, I labeled it homebrew because the receivers were never designed to operate speakers directly, but to use the speaker you had to have a transformer, audio transformer, to transmit the headstone impedances, which is typically around 4,000 ohms, 8,000 ohms. So I had to put an impedance transformer inside the speaker box. So that's why I called it a homebrew speaker, to simulate the LS3 speaker. And the receiver worked perfectly on that. Another interesting thing, this receiver tuned down to 1.6, 1600 kilohertz. I'm trying to stay on the turn. And but it didn't tune the broadcast band. Very few military radios tuned the broadcast band, and I'm not sure if that was on purpose or not. But anyhow, the military people found out that they couldn't tune their local AM stations and wherever they were. Go ahead. So two of the really toughest problems in restoring these radios, this is for a BC-611, which is a Handy-Talkie. And so the big problem with these were that the windings were open. And of course, signal cord doesn't carry those anymore. So we had to figure out, how do we replace that transformer? And so next one please. So I had to put my design hat on. And so I got along with my friend Tom, who's a pro with 3D printing and SolidWorks and so forth. And I figured out how far this spacing had to be in order to make the transformer be properly coupled. So they were just barely overcoupled. And then I put the trimmer capacitor and fixed capacitors. I simulated this on LT Spice also. So I was real confident it's going to work. And so we put this all together, and sure enough, I fixed, repaired, I don't know, 2 or 3 BC-611s with my own IF transformer. And that was kind of a fun little design project on that. But so if you ever have a BC-611 and transformer bad, I can't make one for you, but I can tell you how. Okay, next one. So the other one was really a challenge. A dynamotor in a BC-653 was so noisy that it wouldn't work with the Handy-Talkies. And Russ talked to us about it. He says, gosh, I sure hope we get those working, because he already had the 653 in his command car, and so he wanted to be able to talk to the Handy-Talkies. So he brought the set back to my house. I put it on my bench. I swear I worked for a week trying to figure out why this darn dynamotor was making so much noise into the RF signal. And I finally concluded that the dynamotor magnetic field was energizing the whole cabinet, because this is one of the unusual setups. The dynamotor was inside the cabinet. Anyhow, so Tom, who was with me on these projects, he says, Tom says to me, well, we'll just design a solid-state power supply. And I kind of looked at him and said, 1,000 volts at 300 milliamps? Holy moly. That was way out of my by the way, for HP, I did a lot of power supply design, and that immediately struck me as this is going to be hard. But we set about doing it, and so we found boost converters, of all places, of course, China, for $13, which converted 12 volts to 50 volts DC. So then it was up to me to design what I called an H-bridge converter that would convert 50 volts to 500 volts. So here's the China-built boost converter, and then here's the 50 volt to 500 volt converter. So we built two of those, one on each side of this, and the two together were added together to generate 1,000 volts. And he used his 3D printer. He printed all these parts and put it all together. And the only original part is this plate and these connectors down here, which would plugged into the transmitter. We plugged that in, we got it all set there. So Tom and Russ were all together downstairs, and they said, do we want to try it? So I hooked it all up, pushed the push-to-talk button, transmitted, and the Handy-Talkie was quiet. We were really happy. So Tom and I ended up building 4 of these. And the transformers were handmade. You couldn't buy anything, so I designed the transformer and we built them by hand. So that was really quite an accomplishment to replace that dynamotor of 1,000 volts and 500 volts. The transmitter used both 500 and 1,000 volts. Okay, the next one. Okay, I got some final words here about things. So, important factor of these military radios are really, you would be able to do it, but the military manuals were excellent. Those manuals had theory of operation, circuit description, alignment procedures, schematics, pictorials of wiring, parts lists, and photos. And they were numbered TM11-, for example, TM11-600 for the SCR-508 set. But these military manuals were fairly thick, and they are somewhat available. My friend Russ, he goes to all these military swap fests and stuff, and he buys a lot of this stuff, because most of the military people who restore trucks and jeeps and tanks and stuff aren't too interested in radios, so they would have manuals, and Russ would buy them all up. So Russ was really interested in getting these radios to work in his vehicles that he had. So, and I really want to acknowledge again my friend Tom, who was an expert at the 3D printer and SolidWorks software, and excellent mechanical and electrical skills. And without him, I wouldn't have been able to do such a good job on this restoration project. So one of the things on this is that Russ he has the bragging rights. So when he goes to the swap fest at his military hamfests, if you will, he would talk to those people that have tanks and jeeps, and he would ask them if they had radios that worked. They said, no, we got one in there, but it doesn't work. And Russ would say, yeah, mine work. So he really was proud of my efforts in helping him get that accomplished. Here's some of the radios I restored. I won't read you the whole list. There was about 17 different ones. And I restored, I'm not sure of that number. It may be more, but 48 units. So there's a lot of man hours on that, of all kinds of different sorts of problems. And some of Russ's military vehicles he has a Sherman tank, an M4, an M5 Stewart. He has an M8 armored car, M29 Weasel, WC-53 carry-all truck, a WC-53 command car. He has several Jeeps, and he has some 611s, which are the Handy-Talkies. And Russ sponsors a Camp Bucco right across from where he's situated, and the reactors love to come to his camp. because he hands them working BC 611s, and they really like that. Go ahead. So this has been a very long time resorting project, and I really expect the several aspects of this project I really appreciated. One is it brought me back to my early 50 days when I first started working on radios that are all tubes and living on a farm 7 miles from town, put in a position that I had to learn about like radio electronics. So I was basically self-taught. I built my own test equipment. And by the way, I didn't comment earlier on radio tubes. Those of you who read QAX magazine, I think it's online right now. You can get it, read it. But this last article has an article about radio tubes and how they were designed and built, and it's a very excellent article. So, if you have a chance, read the article about vacuum tubes in the previous QAX and the current QAX magazine. So one of the other things was my Uncle Walter was in World War II. He didn't come back, but I was intrigued to learn about communications for the Army because he was in the Army, and this has been a very educational Army communication experience. Thank you for coming and listening to my presentation. If you have any questions, give me a call.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.